something related to Picard-Fuchs, and actually it's kind of solutions to Picard-Fuchs without Picard-Fuchs. But the main, well, I should say thank you very much for the invitation to this beautiful event, expected event on mathematics and physics. This is the physics, and to have the opportunity to see Aquamatica. That's, so it's an honor to be here and a pleasure. So my talk is going to be about some physics concepts that we are going to explain and try to given some relatively rigorous definitions. So one thing is open correlators. These are the main actors. Open correlators, so that's a word from physics, so that we are going to make it more precise. Open correlators on some gauge, two-dimensional gauge theories called gauge linear sigma models. Sigma models. So I'm writing it to abbreviate it as GLSM and Picard-Fuchs equations, but I should say and applications, because it has more applications than just Picard-Fuchs equations, but in order to attract some audience, I put Picard-Fuchs equations in the title. So I had to explain at least these two big words, and then I will present some conjectures and some uses of them as time allows. So the first part, the important thing is to define this, and then I can go with telling you informally many applications that they have. So this is mostly based, the fundamentals on my works with Kentaro Hori. So we have like two important works on this. So one is a paper from 2013 that you can find on the archive. And we also have a review. So there is a review called, so what says there's some review called Notes on the Hemisphere. You will see why is hemisphere appear here. This review you can find on the internet, but it's not on the archive. So most of the fundamental things are here. And the rest, when I talk about applications, is on many papers that I wrote afterwards. So, okay, so to have the time there. Okay, so let me first talk about what are gauge linear sigma models in a very kind of a very short way. So gauge linear sigma models. So this thing in physics are two-dimensional gauge theories. They are actually supersymmetric. Two-dimensional supersymmetric, abbreviated as SUSY, gauge theories. And I'm going to define the following. I'm going to define something that I'm going to call, or sometimes in the paper we call GLSM datum, is given by a triplet of objects. Okay, a triplet of objects that I'm going to call G, rho, from G to GLV, which we are going to explain, and W. Okay, so we are going to explain these three objects because they are going to appear a lot, and the properties such that G is going to be a compact Lie group, which in the example, if I'm going to do an example in the middle, I hope it's going to be U1 for the example. It's kind of one of the easiest and the favorites. The other thing that we have, so here is this the only requisite for G. There is rho. Rho is a representation. It's actually a faithful representation. So it's a representation, and B is some complex. It's just some complex vector space of rank n. And we are going to call when the representation factors through SLB, we are going to call this situation, this special situation, Calabi-Yau condition, which probably we are going to turn on and impose most of the time. The last object here, w is a function on B called, in physics, we call this superpotential. And we have to ask for some technical properties for this function. One of them is very important. One of them is that w must be is polynomial, so it's like in this space, symmetric, so it's polynomial on the coordinates of V, and it must be G invariant. Okay, that's the important thing. And the other thing that is rather technical for this short talk, but I'm going to talk about this because I need this partially at least. So there exists a series of numbers. So usually they are taken to be rational numbers. So between 0 and 2. Usually we can take it here, but at this point you cannot see. Actually it's okay to take them just between. You can take them real even. There exist these numbers such that w is a quasi-homogeneous function. So Ri, where I is 1 to n, which was the rank of V, and w of lambda to the Ri phi I. These are the coordinates on B, this phi I, and now I choose a basis for B. I write the coordinates like this, and this must satisfy that is quasi-homogeneous of weight 2. Weight 2 is not very important. You can make it weight 1, but historical and practical reasons make me choose weight 2 for all lambda in C star. Okay, so this R is, has a name in physics, this number. This R is sometimes called the R charge. And you may be worried that it looks like there is a lot of ambiguity on choosing this R. It's okay. Now, for effect of this, as long as one set of R's exists, we are good. That's a physics condition, because if I don't have them in this interval, I cannot. There is something that's going to fail. There is some localization that's the following result is. Yeah. This 2 is precisely related with this 2, indeed. Yes. I mean, this kind of numbers also appears a lot in singularity theory. And they also are taken into 0 and 2. But for me, it's just a physical condition that the charges must be between 0 and 2. It's more important usually that they are positive. As long as they are positive, it's okay. But for these purposes, between 0 and 2 is a good condition. All right, so that's what's going to define my two-dimensional gauge theory for practical purposes, as I said. And I need to talk about something else, some properties of this theory, some properties of this data. So this finish the definition. So some properties of this data. So let's write it as remarks. So the remark is the following. The GLSM defined by this data, has two types of distinguished set of parameters. So one of them is going to be mysterious, the other is going to be very clear. So one of them, which I'm not going to use much, but is very clear, is which we are going to call MCS for complex structure. These parameters are going to be like the coefficients, like the parameters, the coefficients of W. So we can set a set of complex parameters given by the coefficients of W. I will set modulo some redefinitions, some redundancies. So these are like if W is a polynomial function, these are just your usual, the coefficients in front of the monomial modulo some possible redefinition of your coordinates, right? So some rescaling, etc. So that's this twiggle. I'm not going to use this much, but this is one important set of parameters. And the other set of parameters is going to be a little bit mysterious, but later on, hopefully this is going to become more and more clear. The other set of parameters is not seeing, you cannot see it from here directly. The other set of parameters, we are going to call it m sub k. And this k is for this set of parameters, actually is called the stringy, because of string theory or sometimes quantum, Kähler moduli or Kähler space. I will call it space, because it's not clear it's a moduli. I mean, there is a moduli problem behind it. It's not clear in this case. So I'm just going to call it Kähler, and I'm going to just indicate that the coordinate on this space, we are going to call them t, maybe a little bit suggestive with some t's that have appeared before. These coordinates t are going to be parameterized. This is going to be parameterized by or labeled by the easiest way is by the center of the Lie algebra of G. You take the dual and you complexify. Okay? So these are just complex coordinates that usually we are going to denote them the real and imaginary parts, usually like notation. So this is just notation. That's going to appear maybe later. Usually the real and imaginary part of t are going to be denoted by zeta minus square root of -1 times theta. Okay? This is, again, this is just notation of the real and imaginary part of this Kähler. So we can call it, usually call t Kähler moduli, but yeah, they come with many names. So this, again, this is just some coordinates in a space. Okay, so that's about this remark, and now I have to say another remark. So there's a 1 there, so there should be 2. So the other remark I have, the other remark requires a definition. So first I'm going to define something. So definition, we are going to define what I'm going to call we define the classical Higgs branch of this thing of a GLSM G, rho, and W at a point theta equal real part of t has the following. So specifying, fix this data and fix this mysterious coordinate, and there is something that's going to be called the classical Higgs branch of this. So what is this classical Higgs branch? Is a pair of things. It's a pair of things. So it's a pair of something that I'm going to call y sub zeta and something that and W restricted to y sub zeta. So what is y sub zeta? Where y sub zeta is defined as the following: mu minus 1 of zeta mod U1, mod G. What is this? So where mu is the moment map associated to rho. So mu is a map from B to the dual of the Lie algebra of G. If you are not so familiar with moment maps, it's okay, because I'm going to write an example soon of this. Okay? So I finished there. I should continue, maybe go all the way back here. So just as promised, so And another definition, let's say another definition is if the intersection of y set with the critical points of W, so these are the critical points of W intersected with y set, is smooth. This is in some cases this can be a smooth variety. We say set or eventually T given by set minus theta haven't played any role so far, but we say set belongs to what we call a geometric phase. So this is physics terminology. But to make connection with what we talked before, when you have this situation, that means set is close to something like a maximally unipotent monodromy point. This K so far is mysterious, MK, but it's going to be identified precisely with the complexified color cone. At least an open set of it, it will be identified with the complexified color cone. And we can show, and indeed, so indeed, when indeed, if let's say this, we can call this x sub zeta. So if Calabi-Yau condition holds, Calabi-Yau condition that's here, this one, then x zeta is indeed Calabi-Yau. So it has trivial canonical bundle. Like you can show if you have this situation that this thing is smooth and also what I call Calabi-Yau condition holds, then automatically this x is going to be, you can guarantee that this is going to be a Calabi-Yau, this symplectic quotient. All right, so in these examples, yes, it will be compact. However, you can have some situations where it's non-compact. Like I can give you a very trivial case when it's non-compact. For example, if your W is 0, identically 0, then you can have a non-compact case. I'm going to give you now one example where this can happen and also include a compact case. So we're going to talk about our working example. So example. It's real. Zeta is real.
One real parameter from the Calabi-Yau variety.
No. It's not. I just didn't put indices. But no. This zeta, remember, this zeta is on the center of the Lie algebra of G. So suppose if G, example, if G is U1, like a product of U1s, let's say S torus, then T here belongs or is labeled by the center of the U1, right? The Lie algebra of the U1s. Well, the center of the, let's write like this, the Lie algebra of the U1 to the S, dual and complexify, and this is just C to the S. So I just didn't write like this. I didn't. So in general, yes. In general, if here you have, for example, this case, yes, this zeta has an index here, and T has an index, and theta has an index, and everything has an index. So it can have multi-parameters. So the example I'm going to write now, it's going to be one parameter, but of course, the multi-parameters is it's a very interesting case. So let me write an example for this. So the example is going to be G equals U1, row from U1 to GLC to the, I don't know, and plus 1, let's say, let's see, n plus 1, yes, that's a good case. I mean, it doesn't matter. It's just to have in my head because you don't know what's n so far. And we're going to have W to be P times F n of x. I'm going to explain all this. So the way this is like P and X going to denote P x1 to xn. This is a point in this in Cn plus 1, right? N plus 1. And I'm going to act rho. I'm going to choose a representation rho of G acting on this point, going to be G to the minus n times P, G times x1, and G times xn. So all of them of weight 1. So G is, of course, an element in U1. So this is my choice of representation. And therefore, W, you can check, is satisfy all these conditions. But I'm going to put one more condition because I need to say what is this Fn, even though you can guess. But Fn of x is homogeneous polynomial of degree n. Of course, it's on x, which has, I choose x to have degree 1, such that the critical points of f is the origin. Okay? So this is kind of a smoothness condition. So I impose that f satisfies. You can take any homogeneous polynomial, it doesn't matter which one, but you have to impose this condition. So it's that will become important for precisely to illustrate this. So now we are ready to look for this pair. So what is y set? So what is y set? Maybe I can tell you, in case you are not familiar, the moment map associated to this representation is going to be very simple. Here the dual of the Lie algebra is just of G is just a real line. So this must be a function that sends you to the real line, and this is just this. I mean, there is a definition, of course, of the moment map, and I'm giving you the result, what you get if you just literally apply this definition in this case. That's the moment map, that function. Okay, right? It's a real function. So therefore, y subset, you can take two situations. You can have two situations here. And one situation is set is positive, and the other situation is set is negative. And set equal to 0 is not a regular point on the level set of this moment map. So we're going to ignore set equal to 0. We're going to concentrate on these two, which are regular. So in this case, y set is this line bundle, OP n minus 1 minus n. So non-compact, but smooth, right? And here is Cn mod set n, Cn mod set n. Yes. So is this singular? So this is non-compact. So if W was 0, then this Higgs branch, this Higgs branch will be smooth here, for example. But we notice that if set is positive, then x set or classical there, the Higgs branch is given precisely by the intersection of what? The intersection of p equal to 0, and so p equal to 0 and fn x equal to 0 intersect with this funny line bundle, right? And this is just a Calabi-Yau hypersurface on the 0 section. So this is a notation, hypersurface of degree n in Pn minus 1. So this restricts you to the base, and then this is the intersection of this with the base. It's just that. So in this case, this is smooth. Of course, it's smooth, but it's smooth because I choose this condition. Not choose that, then this doesn't work. So this is an example of how this two-dimensional gauge theory, just defined by the triplet, is related with geometry. Okay? Very good. So now I need to talk about, so this about this theory, and this was an example how the theory is related to geometry. So now I need to talk about open correlators. Open correlators. So before I should say if there's any question up to here, we are in the 90s so far. We are like early 90s with this in this part of the talk. Okay? Now we are going to go a little bit more in middle 90s. Okay? Maybe early 2000s, a little bit and middle 90s. So this is all prehistory, but of course it's important. I mean, this is kind of a pedagogical talk, okay? Or supposed to be. So open correlators. So what are open correlators? So first we need to talk about some physics nonsense, and then we are going to make the nonsense a little bit with more sense. Okay? So what's the nonsense? So remember that this is a two-dimensional theory. So this is a two-dimensional theory. So the space-time is two-dimensional. So I'm going to choose a particular space-time. So when we choose a space-time, we can compute something called a correlator, which is given by a path integral, which I'm going to denote like this. So this is the space-time. So in order to compute a correlator, you need to set a very particular some space-time. So I'm going to choose a space-time which is just the simplest with boundaries. So the boundaries on the space-time, that's what the name open means in physics. So the simplest space-time is just a disk. Okay. So because you have a boundary in your correlator, you have to choose boundary conditions. So I'm going to choose the boundary conditions. So here there is boundary conditions. Boundary conditions, I'm going to choose them to be of what we call B type. B type, not like bee, like honeybee, but B. We are not going to say, well, I'm going to say something about this B. And in the inside, we are going to perform something that's called an A-twist. This may not say anything to you, what I just draw here. The only thing that's maybe is important to keep in your mind is that there is an A here and there is a B here. So if you are going to talk later about, you are going to ask me if you are in the B model or you are on the A model, it doesn't make sense, okay? So save your question if you're going to say that. So this correlator has nothing to do with A and B model. This is some physical correlator that has a very special interaction between A and B type stuff, which now I'm going to clarify and make it mathematically more sound than just a picture. Okay, so this, by the way, if you want to say who came up with this and that the interesting properties of this, originally, this is also from the 90s, and this was in the work of Secotti and Baffa on the 90s. I forgot the exact date because they have many papers in the 90s, but this is where this started. Then other people make it more concrete. So I should mention, so what this, so the question is, what this computes. So what's the interpretation of such a strange thing? So because the boundary conditions are of V type, that means the boundary conditions are given by these boundary conditions are identified or are given by something called V brain. The reason, if you want to know, is because supersymmetric theories, you have a lot of symmetry, supersymmetry, and when you have boundaries, you cannot have all the symmetries. You have to choose if you preserve no symmetry, some symmetry, a lot of it, very little of it. In two-dimensional gauge theories or two-dimensional theories, you can choose essentially two inequivalent ways, two inequivalent subset of the symmetries to preserve. And because there is two, then you have to call one A and the other B. Okay? So because it's two. You can call it 1 and 2, but someone chose to call it A and B. That was Witten. And of course, we don't discuss with Witten, so we just have to call it B. So in this case, it's the B, which you don't know where it comes from in this context, but I'm going to make it concrete as I promised. So what this computes, what this thing computes. So whatever is this thing is something like a function, I'm going to call Z, something like a function of this B brain that we can call the B brain abstractly B because there is a lot of B's. So yes, so a lot of B is good. So this set of B. And maybe you can add, for the good luck, you can add here a D2 to remember it was on a disk. But what is still is just a letter there, so it doesn't say much. So in order to tell you what is compute, I need to talk about B brains, and B brains, let's say. So B brains are objects, as I said, very abstract, very complicated to compute, but there is a situation where you can make them mathematically sound. Actually, there are several situations, but one that is the oldest and the most well-known. So this situation is V brains. So on a geometric, or you can say on a GLSM that has a geometric face. So on a geometric face, X. Okay, X or X of Z if you want. So what are the B brains on a geometric face? The B brains on a geometric face were identified a long time ago, and they are identified, these guys are identified with the derived category of coherent shifts of X. And here you can delete this, if you want, this set, because this is coherent shifts, so it's like an algebra geometric object. So you don't need to specify this set is more related to symplectic data of X, actually, if you follow up that discussion. So actually, this set is is fairly irrelevant here. So I don't know how much familiar you are with this, but no, okay. But if we want to say one thing, so what are the objects on this category? The objects are, we can think of the objects that you can call them E if you want. You can think of this object as complexes of vector bundles on X. This is not always true, but for X smooth and nice as we have here, we can every object here you can identify with a complex of vector bundles. I assume you know what is a complex from your course of kindergarten algebra, and this is just same thing, but in the factors there is vector bundles. So, sorry? No. It can be made much simpler. Yes, I know what you want. That's coherent shift. No, but at the end of the day, when X is smooth, everything can be a complex of vector bundles on X. That's the interesting thing. So I don't need to add any extra fancy words here. It's literally this. This I'm not fooling you. Okay? And
Kind of a abstract question.
sure. Any question?
Why do people look at the derived category? What is the category of coherent shifts?
Why it's not just coherent shifts?
Yeah, exactly.
That's a very good question. So the thing is, to say it in one phrase, not to confuse maybe people too much, is that if we consider just coherent shifts, we can identify coherent shifts also. I mean, coherent shifts have resolutions, and so they can kind of look like complexes of vector bundles, but not really. The point is, when you have coherent shifts, they are complexes. You can take coherent shifts and then complexes, and they are complexes of coherent shifts that are exact. So, okay, to say even more precisely, when you talk about B-branes, coherent shifts is not enough, because B-branes can form bounded states. Like you can have B-brane supported on X, a B-brane supported on a curve on X, but they kind of can come together. They can interact and create a new thing. How that is translated mathematically? By the fact that you don't consider objects just coherent shifts. You want to consider complexes of coherent shifts. But then if you consider complexes of coherent shifts, you start to run into a problem, which is that there are complexes that are exact. And the complexes that are exact are kind of empty or null B-branes. So you want to identify all the complexes that are exact. And that's what derived does for you. This is very informal. There's, of course, a more formal answer. But roughly, to think of it pictorially, is that you want to identify some of them, and that extra identifications of the complexes, kind of mod out by the exact, is the D. That's what the role that these play. Okay, so I'm doing well. I'm doing well. So this thing, there is, if you take this guy here, now we can compute something. This is an example of a B-brane. So now this set D2B has a very concrete form. This has a very concrete form. And this concrete form is that it becomes an integral over x of something rather complicated. So it becomes an integral over x of e to the omega, which I'm going to say what is omega in a second, which gamma of tx hat, which something called I of I of t, which churn of sorry, let's call this e, churn of e, churn character of e. So I got to say a little bit of what are each of these things. So omega is a point in the complexified, in something called a complexified color cone. So we can think of omega just roughly. It is not entirely true, but we can think of omega. I mean, this is correct, but the limits where omega can go is the part that is a bit complicated. But let's say omega, for simplicity, is like here. It's a point here. So locally, omega can be written as TA of some generators here. So HA, where HA, these are generators of this vector space. So these coordinates, this TA, are some complex numbers that are going to enter this thing I call IT. This gamma of Tx, this is just a characteristic class. It's just a multiplicative characteristic class based on the gamma function. You can base characteristic classes on many functions. You can make one out of the gamma function. That's called gamma class. Is what entered here. So there's no parameters here. There is parameter t here. And there is parameter t also here. So this IT is very mysterious. This IT is a cohomology. So it's a cohomology valued series series in e to the t. Sometimes it's called I function. It was discussed by Giventhal. And if you are familiar with the numerative geometry, if not, what I said doesn't make much sense. This is like generating function of something called quasi-maps. Quasi-maps are similar to Gromov-Witten invariants, but not quite. They are related, but this is kind of the quasi-maps enter there. If you don't know what quasi-map, it's okay. It's this. It's a commally valued series in e to the t that was defined. It has a concrete definition in terms of characteristic classes, etc. It looks in some examples like a cohomology valued hypergeometric series. In some examples, like in the examples like hypersurface, this looks like a hypergeometric series, but I'm not going to write it because it's very complicated. And finally here, as I promised, if this is a complex of vector bundles, you can take its Shen character, which is also cohomology value, and that's there. So very horrible thing, very complicated thing. Now, how can I identify this with something that appears before in the previous talks and maybe more familiar with you? So if I take the mirror, mirror of x, so let's call this x zeta or x check. Now this zeta becomes complex structure parameter here, because that's how the mirror works. So let's say there is another geometry. This is a smooth geometry. The mirror is most likely to be another smooth geometry. So this is the mirror. Here, I'm not going to talk about A-branes on the mirror, but there is something I can compute on the mirror that's exactly equal to this, maybe up to a change of variable. And this thing is this x, right? This thing is a period. It's a period over some L, and L, here L is the mirror of E, whatever that is, whatever the mirror maps to. So, good? Okay. So this is the important part. This is what it computes, and this is how it looks on the mirror. Okay? So this is called, and in physics, this thing has a name. It's called the central charge of E. Okay? So now, where there is a e to the k over 2? Where? Sorry. E to E? This is holomorphic. I remove the e to the k. These are holomorphic. These are not invariant on the monodromy either. These are literally the periods. This is a holomorphic function. It cannot have the e to the k.
So where is the ambiguity on the left-hand side? The scaling ambiguity on the right-hand side? You have freedom to rescale the holomorphic 3-4 on the right-hand side.
Just by a constant.
By a function.
X is smooth and compact. If X is non-compact, then to make this match is a bit complicated.
You can rescale it, but yeah, so by a constant it becomes a function when you vary parameters. So you can scale it by a function and complex structure parameters.
This one.
Yes.
Yes, so if X is compact and smooth, that function has to be constant, right?
Yeah.
So if X is non-compact, then the answer to the question is a little bit more tricky.
I mean, it's a constant for a fixed value of complex structure.
Yes.
It's a constant depending on the complex structure. So that you can, so it's a function of the complex structure. Where is the ambiguity on the left-hand side?
Oh, you can also rescale this by a constant, but there is something. Yes, there is something to suspect on this equation. There is something not very good in a sense that you have to. That's what I was going to say. So you have to be a little bit careful with this equality, and the equality is precisely that this is kind of a global expression on complex structure. This integral. This is not. This is not because I use the word series. It's actually a power series. So the complex structure, so here I'm only working on a cone. So I think on that cone, the ambiguity is just the same for every point on that cone, or not. I think for the color, if I restrict myself to the color cone, which is implicitly happening here, I think the ambiguity is the same. You don't agree with that? Okay, that's a discussion for Aquamatica. That's okay. Let me give you the punchline, because let me give you the punchline of this otherwise. Yeah, I don't know if there is more ambiguity than that, than just a constant in front of. Okay. Maybe I know the answer to your question, but I think I may know what you have in mind, but I'm not going to. I think that ambiguity is secretly is on the R charge, on the choice of the R charge actually. But I will give you kind of a partial answer with the following slide. So the question is how what was our result? So our result. So the result that we had with result of Jorge and myself. What was this result? So I should mention the result is we found a way to compute exactly, to compute set D2 of B-branes for any gauge linear sigma model. Yes. So I'm going to write you, instead of writing the general formula for this, because it will be a mess and there's no time, I'm going to write you the formula in the example. So you will see what is T everything on that example, okay? So in order to write it, we are going to do an example. So the example is, again, this hypersurface case. But now I don't need to talk about the hypersurface particularly. Like I don't need to limit my T or my theta to this geometric phase. I just start with this data G, rho, and W. And from that data, I construct this function. So this function, in this case, is going to be set D2 of B. And what is B on this GLSM? This is kind of one of the hardest part to define, but let's first write the function, then I'm going to talk about B. So the function is going to take the following form. It's just some contour inside C. I'm going to write sigma for the coordinate on C. And there is some contour, and then there is E to the square root pi of 1 T times sigma. This is the same T as before. And here there is something like this. Minus sigma, yes, to the n. So there is notice here, I'm not going to send, but there is a choice of these Ri's. So you take this form times something that depends on B, Fb of sigma. So this is the only, so the form is this one. It's like a Mellin-Barnes integral. So this is always the case. So this is something called a Mellin-Barnes integral. Okay, And I only have to tell you what is this, how you get this B. So the problem here is that because I don't start from the geometric data, I start just from this GLSM data that is here. I have to kind of think a little bit what is B, because I cannot just say it's the derived category of coherent shifts on whatever is this vector space here, or I don't know, G, etc. I mean, I have to say more clearly what will replace the V brain. So in this case, V belongs to it's kind of the natural category, but this you can compute. Of course, what is the natural category that replaces the derived category of coherent shifts in this case, and that's the category of matrix factorizations with a U1 equivariance of W. Okay, so you may not be familiar with the category of matrix factorizations, but the category of matrix factorizations, to say it in like 5 minutes maybe a little bit less, you can think of these matrices as objects here like matrices. So matrices, so there's some endomorphism on some vector space I call M, which I'm not saying what it is yet, but there is some matrices. These are matrices, and there is something I call rho M, which is some action of the gauge group on whatever vector space these matrices act on. So with the conditions that T square is W, this function W times the identity on M. Again, M is some vector space, and rho M, I'm not going to write the equation, but is compatible with rho of rho from G to GLV. So it's compatible with the rho defined on this GLSM data. So there is a compatibility condition. So once you have this, then you can define then FB of sigma is given, has the trace over M, is given by a character, essentially, is given by a character, or I will call it the super trace. There is a weight here. There is a set to weight, which I didn't specify, but it's a weight, it's a character or super character of this rho M of e to the 2 pi sigma. Okay? So that means generically, that means generically, this will have the form. This will have the form. This will have the form of some e to the 2 pi QA or QI sigma with I from 1 to the dimension of M. And there possibly here, because of the super trace, there is possibly here some e to the I pi to some Ri's. So in this example, in this example, like these QIs and Ri's are both in the integers. So these QIs are like the weights of this action that you have to specify. So the punchline, let's say, is that maybe this is time to make a remark then. The remark is that all these guys can be written in this form. So they always take the form of a Mellin-Barnes integral. And they are always mirrored to periods, to period function. So because of this equality here, so maybe I should say the remark. And with this, I finish. So about the properties. So remark on the properties of this function is that this one there, this function here, this function, let's call it star. So the function star, as you expect, satisfies a linear ODE of order, in this case, n minus 1. Let me see, yes, that's correct, of order n minus 1 for all choices of B. Maybe that's one. So, and this linear ODE, this linear ODE is precisely, I mean, if we compute it, if you take this, this quantity, this linear ODE, this, in order to use the word, this is precisely the Picard-Fuchs equation. And maybe the second thing to remark for the people that like these categories, and with this I conclude. That's right. I didn't write it just because. Okay. Yes. It's here. It's just for time I didn't write it, but you can ask me in Aquamatica about it. I mean, it's exactly what you expect, by the way. And the second is that this derived category of coherent sheaves of etc. Is how it is related to this mysterious maybe category of matrix factorizations of W. And the way it is related is that this can be embedded in multiple ways here. So there are multiple embeddings. So this K is like some label. So there exist multiple embeddings. So they are not equivalent, but there exist multiple embeddings. And this can be used actually, the relation between the embeddings, and this is the last thing I said, the relation between embeddings can be used to compute exactly. So no numerics here. This is like really an exact analytic computation. Monodromies of that function of set D2 B along loops in MK. Okay. So with that mysterious remark, I finish. Thank you very much.